Thank you everyone for showing up virtually. I'm going to be talking about tipping points in melting beneath Antarctic ice shelves. And this is an update on a presentation I gave for our team at the November meeting. So I'm going to start by summarizing what I presented then and then go on to work we've been doing subsequently in the last 6 months or so. And this is work done by the entire Cryosphere team, and I've listed the names of people who've contributed specific large contributions to the work I'm showing here, but there's additional members of the team beyond these people as well. So it's definitely a group effort. And I've subtitled this A Tale of Two Ice Shelves because the talk will focus on the two largest ice shelves in Antarctica, the Filchner Ice Shelf, commonly abbreviated FRIS, and a little bit about the Ross Ice Shelf. And this plot on this title slide here just shows the melt rates for all of the Antarctic ice shelves simulated by E3SM. And these melt rates simulated by E3SM turn out to be quite a good match to current observations. So while there's lots of interesting things to say about all these other small ice shelves, this talk will just focus on the two big ones, primarily Filchner. So the outline is I'll give a little bit of background on Antarctic ice shelf melting. I'll summarize what we've already know about ice shelf melt tipping points in E3SM, largely from my talk in November, and then proceed to discuss things we've done since then, which is looking at the impact of improving ocean eddy parameterization through the so-called 3D GM version of MPAS Ocean, and looking at results for our E3SM V2 mesh, which has regionally refined around the Southern Ocean. So for some context, we know that ice shelves are the primary control on the sea level rise contribution from Antarctica. So on the left here, you can see that the ice shelves that extend out from the grounded ice are in contact with the ocean, and the ocean carries a lot more heat than the atmosphere. As the ocean melts these ice shelves and thins them, it reduces the amount of back force or buttressing they provide on the grounded ice. And as the ice shelves thin and the grounding line retreats, the flux across the grounding line into the ocean can increase, in some cases, unstably. And so the ice shelves are really the gatekeepers of the Antarctic grounded ice sheet, and therefore a key control on sea level rise. And this figure on the right, you can see that it shows the ice shelves here are all colored by their thinning rates, and these gray circles indicate the amount of mass loss from that sector of the grounded ice sheet. So where this is large, these circles that are large, you can think of that as a large sea level rise contribution. And you can see where the ice shelves are thinning rapidly in these red areas, you have a corresponding large loss of grounded ice or a large sea level contribution. So we have observational evidence that this is already happening in the real world. So conceptually, we can think of Antarctic ice shelves as either warm or cold, and there's a kind of bifurcation point of two stable states for an ice shelf in either this warm state or a cold state, and there's very little in between states possible, or there's only in between these two end states, there's only a transitory pathway. So whether an ice shelf is warm or cold is determined by the access of circumpolar deep water to the continental shelf and to the cavity beneath the ice shelf. We can see that in this map showing ocean temperatures at the seafloor on the continental shelf around Antarctica. Most of the continental shelf has relatively cold temperatures close to the ocean freezing temperature. But in this Amundsen-Bellinghausen sector, we have warm ocean temperatures, and that's entirely due to the access of circumpolar deep water, or CDW, onto the continental shelf. And correspondingly, you can see that observed ice shelf melt rates, track very closely to the temperatures of the ocean water on the continental shelf. So you can see both Filchner and Ross have low melt rates, and that's because in present climate, they're in contact with cold continental shelf water. However, if CDW is able to access the continental shelf and ultimately get underneath the ice shelf cavity, which would be this region here, it can activate what is sometimes called the ice shelf melt pump. So in a cold state, you have a warm pool of circumpolar deep water off the continental shelf and cold water in contact with the bottom of the ice shelf. If for whatever reason the circumpolar deep water is able to spill or intrude onto the continental shelf and makes its way back to the grounding line, then that increases the melt rate, and the plume of meltwater creates a vertical circulation cell that pulls in more warm circumpolar deep water as a positive feedback. And once that melt pump gets activated, it's extremely difficult to turn off. You could remove the perturbation that initially allowed CDW onto the continental shelf, but this melt pump would continue running. So you have these two stable states that can be triggered in what is a very clear climate tipping point. So to investigate these issues, we've been primarily using the E3SM V1 low resolution cryosphere configuration. For the first part of the talk, I'm going to focus on G cases, which are ocean and sea ice only with the data atmosphere. And what's unique about the cryosphere configuration is the inclusion of cavities beneath the ice shelves. So in the default version of E3SM, there is basically a vertical wall at the front of the ice shelf. But in the cryosphere configuration, we resolve this cavity, and the ocean model can circulate in that area. So I'll point out that right now we're using fixed ice shelf cavities where the geometry of the ice shelf doesn't change, and there is not an active ice sheet model, but we are currently working on improving that coupling so we can have an active ice sheet model that will allow the cavity to change shape as time goes on. And there's kind of two flavors of runs I'll be talking about. ISMF is an abbreviation we use for runs that include ice shelf melt fluxes. And there's a second run where we've disabled ice shelf melting in this sector of Antarctica, but included it around the rest of the continent. And that's called ISMF-noEAIS for East Antarctic ice shelves. So we see CDW intrusions in most of our simulations onto the continental shelf in the Weddell Sea in front of the Filchner Ice Shelf. That eventually intrudes beneath. Here's the ice shelf front. So this is all the ice shelf cavity. And once that happens, we get runaway increase of the melt fluxes due to that melt pump activation. So this time series on the bottom shows the melt flux for the entire Filchner ice shelf over time. These colored dots indicate approximate observational estimates of present day melt rates. So you can see E3SM is doing great for about 100 years, and then suddenly, like a switch being flipped, melt rates increase by over an order of magnitude. And this has not been observed in real life. And so this is preventing us from being able to run. So this is occurring in both historical and pre-industrial runs that we've done. So this is obviously a problem for the realism of the cryosphere configuration. So I'll give you a bit of a spoiler alert. We found we can prevent this runaway melting from occurring in two ways. One is disabling melt from the upstream ice shelves in the East Antarctic region I indicated. And a second is by reducing model biases in salinity through improving the eddy mixing parameterization. So I'll touch on each of those solutions in the coming slides. So this slide is a bit busy, but if you follow with me, I think it will be quite instructive. These are plots of temperature, salinity, and northward velocity at the location of this star which is at the break of the continental shelf to the deep ocean in front of Filchner Ice Shelf. And you can see this is colored by bathymetry. You can see there's this deep trough running from beneath the ice shelf all the way out to the edge of the continental shelf. And so this is the low point in the continental shelf, and this is the easiest place for CDW, which exists out here, to intrude up onto the continental shelf and enter the ice shelf system. So this is a key location to assess, and all of these plots are showing depth profiles over time, in this case about 130 years. And here at the top you can see the melt rate time series, again at observationally observed rates for about 100 years and then jumping up very quickly. And what we can see is when the melt rate jumps up, it's preceded by a reversal in the flow direction. So the red means water's flowing from south to north or off of the continental shelf, and blue means it's flowing from north to south, so off from the deep ocean onto the continental shelf. So we see these blue regions that are intrusions of what turns out to be very saline and warm water, which are the indicators of circumpolar deep water. So each of these clusters of warm water, warm and salty water at depth, is a intrusion of CDW getting onto the continental shelf that lasts a few years. And these types of intrusions have been observed by in situ oceanographic and mooring data. But what happens is eventually, if those intrusions are persistent long enough, the melt pump activates and you get a sustained high, sustained inflow of CDW that starts increasing the melt rates at the ice shelf. So that's kind of what we can learn by this analysis right at the Filchner Sill, this red star location, and I'll come back to that later in the talk. So I've mentioned this run where we disabled ice shelf melting in this region, which is upstream because the Antarctic's coastal current travels counterclockwise and is advecting water from these ice shelves towards the Filchner Ice Shelf. So if we disabled melting from these ice shelves, and we did this by a branch run at year 50, and then we continued that out for another about 70 years, and what you can see is the CDW intrusions that were happening regularly and then became sustained are much reduced in magnitude and duration, and the tipping point never occurs. And we've continued this run out another 50 years, which I don't have shown here, but there is no increased activity in CDW intrusion. So this has the effect of disabling this tipping point from occurring. To understand this a little bit better, we can look at the difference between these two runs for the 50 years or the 60 years that were starting at year 50. And this first plot in the upper left basically shows the production of fresh water from ice shelf melting that is coming from these upstream ice shelves. And then these three other plots are showing salinity at different depths. And you can see that the inclusion, when these ice shelves are allowed to produce melt, it's creating much fresher conditions in the wet LC, and that that low salinity signal begins to accumulate on the continental shelf in front of the Filchner Ice Shelf. Yeah, so this kind of blue that gets darker over time. And eventually that suppresses the density enough that it allows the onflow of circumpolar deep water from offshore. So we're not entirely sure the exact mechanism at the Filchner Sill. Clearly this freshening on the continental shelf is key, but it's not clear yet if the exact mechanism is changes in the gradient, the density gradient on the shelf versus off the shelf, and if this is a density-driven flow, or if it's something a little more complicated related to changes in vertical stratification and/or changes in baroclinicity of the flow on the continental shelf and at the ice shelf front. So these details are something that we're continuing to work on. So the summary so far is we've identified that glacial meltwater can create freshening on the continental shelf that allows for CDW incursion and runaway melting at Filchner Ice Shelf. And to just kind of explore the implications of this, we did a ice sheet model simulation with the MOLLE ice sheet model in E3SM, and this is a standalone MOLLE simulation, but we increased the melt rate beneath Filchner Ice Shelf by a factor of 10 and looked at the effect on sea level rise and mass loss from the continent, and it resulted in about a 10 centimeter sea level rise in 200 years. So it's a pretty significant impact if this event were to occur in real life. So moving on, I want to now update you on what we've been doing since this previous work I had discussed a bit in November. And the first topic is using the recently improved three-dimensional version of the Gent-McWilliams parameterization for ocean eddies. And this is commonly referred to as GM. The GM ocean eddy parameterization is used at coarse ocean model resolution where eddies are not able to be resolved, and they represent the missing eddy-induced velocity that you would have if your model was at a fully eddying resolution. So historically, MPAS Ocean has used a GM strength that is constant in space, and recent improvements, largely by Luke and others on the ocean team, have allowed a more realistic implementation where the GM strength varies three-dimensionally. So we've tested this new version on both G cases and B cases, and I'll show that now. So very exciting result is that when we switch, so this red line is the run with runaway where the tipping point is triggered after about 100 years in the G case. And the black line is the exact same run. The only difference is we've turned on the three-dimensional version of the GM coefficient. And you can see that when doing so, the tipping point is avoided and the model runs stably for as long as we've run it, which is getting close to 200 years. So also exciting is now I'm showing you results for a B case with active atmosphere. And historically, we'd found that our B cases had the tipping point triggered even faster than in the G cases. So B cases were almost useless to us. But we found with the 3D GM implementation, again, we avoid the instability that in this case had happened around year 55. So these B case results are still preliminary. There's some incorrect atmosphere settings that were on the version of master we were using at the time, so we need to rerun those. But we're cautiously optimistic that this improved behavior will hold with the once we complete the runs with the corrected atmosphere. And just kind of looking at a few details, we can see that the salinity bias, and here I'm showing sea surface salinity, is vastly improved with 3D GM. So this is, I'm showing the bias, so the difference between the model versus observations. And our original B case was very fresh, especially in the wet LC. And with 3D GM, we still have a fresh bias, but it's not nearly as bad. And as we saw earlier, this salinity control is key for this tipping point activation. So anything that reduces the fresh bias should help things remain more stable. And then going back to this plot I like so much that hopefully people have been following. In the upper half, I'm showing the version I showed you before, and then in the bottom version is the version with when we've turned on 3D GM. And you can see that the velocity is always northward, except for brief seasonal variations where maybe you get a little bit of southward flow, and there's no evidence of, or there's very little evidence of incursions of warm, salty water that would represent the circumpolar deep water. And then you can also clearly see that this salinity plot in the old run was much fresher than the new run, and that's the reflection of the reduced bias in salinity. So the 3D-GM also improves the seasonal cycle, and I mentioned that briefly on the last slide, but this plot here shows observations from a mooring located near the Filchner Sill, just showing the seasonal signal of CDW incursion every austral fall. So these red blobs are the CDW coming in, and here I've scaled it to the same size as these plots, but you can see that this seasonal cycle here looks a lot more like this than more like the observations than the previous runs that did not include 3D-GM. So not only is the bias reduced, but the seasonal cycles improved. And we can also see that the 3D-GM is blocking these CDW intrusions much more strongly than disabling melt did. So what we're looking at here is a transect across the Filchner Sill. So this is the entrance where CDW is pushing into this trough. And what we're looking at in the upper half is the, again, northward velocity. So red means water is flowing off the continental shelf towards the deep ocean, and blue means water is flowing southwards, which is likely CDW intrusion from the deep ocean onto the continental shelf. So this is at year 99, which is right when the tipping point initiates. And in our original ISMF run, you could see this clear signature of southward flow, which is indicative of CDW, and you can see the warm temperatures associated with that. When we disabled melting from nearby ice shelves, we prevented that southward flow, but you could still see that the northward flow in this eastern part of the trough is reduced, and there's still the presence of warm water. But with 3D-GM, we see a very vigorous northward flow and very little sign of warm water appearing. So it's not clear if the 3D-GM run is necessarily closer to observations. We still need to kind of figure out what exactly is the correct strength, but we see that this is a very strong control on the axis of CDW. So for the final part of the talk, I'm going to talk about the second area of improvement we've been working on, which is using our starting preliminary runs using the Cryosphere campaign version 2 mesh, which is regionally refined in the Southern Ocean. So we call it the Southern Ocean Regionally Refined Mesh, or SORRM. And this is the first Cryosphere campaign mesh to truly exploit regional refinement. And I should point out that this is what we would call a R0 or mesh revision 0 attempt. And we expect to have some minor tweaks or adjustments to this going forward, including, for instance, we're testing some meshes that have the region of refinement a little more complex to reflect the complexities of the geometry rather than just an annular shape. And this mesh has about 3 times as many cells as the low-res mesh I've discussed so far, but it's refined to 10 kilometers through most of the Southern Ocean, whereas the low-res mesh only had 30 kilometers. And that allows the simulation to be eddy permitting through the majority of the Southern Ocean, and it also allows us to much better resolve a lot of the small ice shelves that I mentioned in the first slide. So initial results were that when we started running this SORRM mesh, we were happy to see that the Filchner Ice Shelf melt rates appear to be stable for the first few decades. But then we were very surprised and somewhat frustrated to discover that suddenly the Ross Ice Shelf has become unstable. And this tipping point in the Ross Ice Shelf gets triggered after only 16 years. So this was pretty frustrating, although also very interesting to discover. And when we dug a little bit deeper, we discovered that we had an incorrect setting for the Club V2 eddy mixing parameter CK10, which I imagine many people on this call are very familiar with this specific issue. And once we corrected that value, then the simulation avoided seeing the tipping points at the Ross ice shelf. So the kind of takeaway here is that this ice shelf melt tipping point instability is maybe very sensitive to atmospheric forcing. So one thing our team is going to be doing going forward is working more closely with understanding what's happening in the atmosphere in our B cases. And while this was a bug and inadvertent, it was also kind of an interesting experiment to understand what would lead to a tipping point in the Ross ice shelf, which there have been a high-profile study highlighting the potential for the Filchner ice shelf to reach a tipping point, but there have not been any model studies indicating the potential for the Ross ice shelf to experience this. So this is actually pretty intriguing from a cryosphere perspective. So looking at the difference between these two runs where this club eddy mixing parameter was fixed, we see very large air temperature differences in the atmosphere. So this is in the first in years 2 to 6, the middle is years 11 to 15, and the left panel is years 16 to 20. And you can see we're pushing a 15-degree difference in air temperature after 15 to 20 years between these two simulations, which is huge. And most of that warming is centered in the Amundsen and Ross seas here, which if we also see that winds are more onshore in the Ross sector. And when we look at sea ice, we can see that the run with the incorrect club parameter has a vastly decreased sea ice cover near the Amundsen sea coast relative to the correct parameter value and relative to observations. So this is obviously a coupled problem, and it's unclear if increasing temperatures are leading, a 15-degree temperature increase is leading to decreased sea ice cover, or if decreased sea ice cover is changing the atmosphere boundary condition and resulting in warmer temperatures. And these are very new results, and we're still sorting through the details of the mechanisms. We also see that in the run where the Ross, with the incorrect settings, where the Ross ice shelf reaches its tipping point, we have a significantly stronger coastal current. So that could also be potentially responsible for redirecting warmer water towards the Ross ice shelf. And kind of the smoking gun is that we see ocean temperatures at the sea floor we can see sorry, my mouse is stuck. Well, hopefully you can see where the arrow is pointing, that the warm CDW has kind of fingers of warm water intruding underneath the Ross ice shelf, which is the signature of the tipping point and melt pump activation. So to summarize where we're at on the cryosphere team is that for the last few years, we've seen that E3SM tends to trigger a tipping point in Antarctic ice shelf melting. And we have identified that melt from upstream ice shelves is a factor that can contribute to this tipping point, which is something not previously identified by other modeling studies. So this is pretty exciting to identify the prospect of ice shelf melt teleconnections and potential for some sort of domino effect between different ice shelves affecting each other's melt rates. More recently, we found that this new 3D GM parameterization greatly reduces the biases that lead to the premature activation of the tipping point. And this is very exciting because it now gives us a path forward to doing all of the pre-industrial, historical, and future scenario runs that we would like to do on the campaign. And then finally, the version 2 regionally refined mesh appears stable and will provide us with 3 times the resolution in the Southern Ocean. And through an accident, we also discovered that the activation of these ice shelf tipping points is very sensitive to the atmosphere model. And that's kind of an interesting coupled problem that we'll want to explore more going forward. So for my final slide, I'll just kind of mention where we're going from here. So our ongoing work is to finish the analysis and writing up a paper on this ice shelf melt domino effect that I talked about at the beginning. We're going to continue our pre-industrial control with the 3D GM settings, and that will allow us to complete the model description paper for the Cryosphere V1 configuration. And like I said, finally permit us to begin pre-industrial, historical, and future scenario runs for the Cryosphere campaign, assuming that the pre-industrial control continues to avoid triggering this tipping point. So fingers crossed on that. And then we'll be finalizing the SORRM mesh and hopefully at some point beginning production runs for V2. And along the way, we've run into some interesting ideas that we hadn't really considered going into this. And one thing we would like to do, if we have time on the team, is to investigate both the regional and global climate impacts of the freshwater flux increase that occurs after a tipping point in the Filchner ice shelf. So what I didn't say is when that tipping point occurs, it approximately doubles the freshwater flux from the entire continent of Antarctica to the Southern Ocean. And due to the connectivity of the Southern Ocean with the global ocean, there's a potential for global climate impacts due to this very, very local effect. And now that we discovered the Ross ice shelf also has the potential to trigger a tipping point, it would be very interesting to investigate if the regional and global climate impacts associated with a Ross ice shelf tipping point are different than those associated with Filchner. So I'll stop there and I'm happy to take any questions. Thank you.